All right. Good. So last time we finished the description of the basic canonical quantization or operator formalism. So we've seen how to write Feynman diagrams and what those imply for the correlation functions in the operator formalism. But as I said, there are two formalisms for quantum field theory, and actually for quantum mechanics in general. There's the operator formalism and the path integral formalism. And today we're going to take the first steps towards understanding the second path integral formalism. We've reviewed how to write a path integral for quantum mechanics, but that was kind of first approximation, a very hand-wavy one. And also, when we reviewed the path integral formulation for quantum mechanics, we saw that we needed to introduce a function, J, that in turn meant that we can write a generating functional for the correlation functions of quantum mechanics. And as we saw, the correlation functions are the things that we really want to understand. So that means that we want to write these path integrals with the introduction of this additional function. All right, so let's start with this setup. And we will see that, so today we will describe quantum mechanics, and specifically, as I said, the simplest quantum mechanical example is the harmonic oscillator. And if we understand that in well enough, in enough detail, then we're able to generalize to quantum field theory easily. And the harmonic oscillator will be driven or forced, which is the statement that we need to introduce this function J, as we will see. All right, so what did we see? So let's remind ourselves. We were looking at an amplitude for a transition between the state is Q prime at time T prime and the state is Q at time T. Yeah, I guess Q prime T prime Q T. So these were Heisenberg operators, so that means I'm just showing a picture. There were, Heisenberg states, which means in the Schrödinger picture we had this. And then we were able to rewrite this transition amplitude as a path integral over phase space dq of t, dp of t, and then an exponential which is p of t, q dot of t, minus the Hamiltonian this, of course, being the Lagrangian, so its integral being the action. Okay, and then t0 to tn minus 1 was because we took a path and we divided in n plus 1 intervals. And that's what this path integral meant. We meant the integral over all the intermediate points qi of t. Then we saw that if the Hamiltonian is quadratic, so if h is p squared over 2 plus a potential v of q, which is the usual form, then we can write the amplitude in coordinate space. And we obtain in general some normalization constant, something that is independent on the variables, times this path integral path integral of dq, exponential of I times the action, which is a function of this q of t. But then we saw that the things that we wanted to calculate in general, I mean, for quantum mechanics, this, as I said, would be sufficient. Quantum mechanics deals with single particles that don't interact with other particles. So the path of the one particle is the only thing of interest. So in principle, this would be enough. But in order to generalize to quantum field theory, it is good to consider these endpoint functions which were defined as were defined by the insertion of the time order product of q of t's inside the same product of Heisenberg states. And then this itself became the same path integral, but with the insertion of the same dq's. So e to the is q of t, but then insertion of q of by 1, q of t by 1. Right. And then even further, we solved by the general mathematical fact that if you have a set of numbers, or functions in this case, you can put them together in one generating function, or in this case generating functional. So we defined this generating functional, and we called it z of j, as the path integral of something we call s e to I s of q and j, which is just adding a term to the action, which is I integral q of t, j of t. Okay? And in so doing, as usual, the endpoint functions, the things that we want to obtain from the generating functional, are obtained by the nth derivatives of the generating functional. At j equal to 0. Okay? So, so this step of introducing the generating functional by adding such a term, at this point was just a mathematical trick. The fact of conveniently putting together all this bunch of functions into a single functional. However, now that we have this, we see that we have the combination s of q and j, which, so I is common factor, which is s of q plus integral q j. So now we have s of q and j as s of q plus integral q j. And then we see that from the point of view of this combined action, s of q and j, this term acts as the source for the dynamics of q. That is an external driving force. That is the driven or forced in the title, because then if we write the equation of motion of this new action, is the equation of motion of the original action, but then plus j of t. So now ds of q dq of t is minus j of t. So that's really what is meant by saying that this is a source or external driving force for the system. And specifically, we will talk about the harmonic oscillator, so the action will be the action of the harmonic oscillator. So that means S of Q and J is the action of the harmonic oscillator, q dot squared over 2 minus omega squared q squared over 2, but then plus this extra term. Okay? Okay, and of course, as before, the importance of the harmonic oscillator is that the action is quadratic, which means that the path integral is Gaussian, so we can do it exactly. So that's still the case because the term we added is linear in J. So it's quadratic in J, in Q, sorry. So that means that we can solve, we can do the path integral exactly. As it is Gaussian. However, there's a subtlety, as we will see. The issue of boundary conditions. You have to remember now that this is a functional, not a function, and the space of functions on which this is defined is important, in particular the kind of boundary conditions the functions obey. All right. So let's try to understand that. So we'll do this in two steps. First, we'll do a more sloppy treatment that is meant to emphasize the general theory behind how you do such a path integral. And then we'll do a more correct treatment, which, although is more correct, it will appear more involved, so it will be harder to follow. But once we have the understanding from the first, it will be easier. So let's start with the sloppy treatment. Okay, so this is our action that we must consider. And now, if, and that is actually the point in question, if we can do the partial integration without boundary terms, then we would write this in a form like we're used to from Gaussian integration. So we would write this as minus a half q of t, then an operator, which in principle we can think of as a series of numbers, if we have the operator act on some eigenfunctions. So that's why in principle we could use the Gaussian integration formula. And then another q of t, and j of t, q of t would be a linear term. Okay, so from this point of view, so this is some operator, but by acting on eigenfunctions q of t, I could in principle think of it as a series of eigenvalues for those eigenfunctions. And then in principle I could use...
So does it make sense to think of this operator as diagonal? Doesn't make sense?
Well, yeah, so we have to first diagonalize, so let's consider that, yeah. So in principle, this would be of the form right? So here I said that IS I've written this as this form, right? Perhaps that's more. Okay, so is in principle is of this form. It's minus a half q something inverse q plus I jq. Well, so this is S, but IS is written in this form, right? So right. So first of all, yeah, this is not diagonal. This, well, okay, the operator itself, the issue is whether or not it's diagonal. It looks diagonal in the sense that if we find eigenfunctions, then its action on eigenfunctions will give a number. But then moreover, we have the issue of diagonalizing the matrix itself appearing in between the q's, because as it is not. It has this off-diagonal term. But first of all, let's look at the operator itself. So by our definition, this delta minus 1 of q is, so delta minus 1 of q stands for the term in IS, so this is I times this thing, right? So I times d squared dt squared plus omega squared acting on q of t, right? Yeah, and then here j dot q is integral dt j of t q of t. And of course, delta will stand for the propagator. It's not a random choice of letter. But, well, assuming these definitions, once I've put it in this form, then we would use just Gaussian integration. Right? So we wrote the general Gaussian integration for something of this type, right? For an action that was 1/2 a vector times a matrix times a vector plus vector times vector. And then we saw that this Gaussian integration led to, so one was co-determinant of A and the free term the term.
We discretize it first.
I'm sorry?
We discretize it first. Lecture 2.
Right. That's right. So, but that was also part of what we meant, because the path integral, remember, was defined by discretization. Right?
Yeah.
The path integral itself is understood that it means a discretization and integration over all the discrete points in between.
And now you are discretizing, or how do you separate?
Well, no, I mean, so the path integral is the discretization. There's no difference between the two, right? That's what I mean.
But the separation that you do, so how you put the integrals, how you divide. So, for example, there that's the propagator acting on a QFT.
Mm-hmm. Just wait. I mean, if something is unclear, maybe it will become clear later. But as I said, this dq of t, it really means path integral really means integral of qt1, qt2, and so on, right?
Yes, but my concern is how you discretize in this case the functional, because it's not so straightforward as like you should.
Okay, I don't understand what you're doing, but let me go on, and maybe if you have a question, you can ask later. So the result of the general Gaussian integral is 1 over square root determinant, right? Then there's the factors of pi, in this case 2 pi to n over 2. And then the free term that comes after diagonalizing this. So there's a quadratic term that is Gaussian integrated over, and then there's a free term that is this one, right? Okay, so so we can apply this general form, this general formula, and now we see, so this is our form versus this one, right? I mean, this is IS, right? Corresponding here to minus S. So let's be very clear. So in the exponent, we have e to minus a half I q delta minus 1 q. Minus a half q delta minus 1 q plus I j q versus e minus a half x transposed a x plus b transposed x, right? So then b is ij, so q is x, of course, then b is ij, and a is delta minus 1, right? So that's our mapping. And then the result of the path integral is, well, there's a bunch of numbers, which remember that I don't care. Anyway, I have an overall number, normalization constant, and so all of these 2 pi's and stuff and i's, I don't care about. I'll only be interested in the functional dependence. Then 1 over square root determinant of delta minus 1, and then this exponent. Okay? So now this 1 over square root determinant of delta minus 1, this would in principle be, so the delta minus 1 is also independent of j. Remember, the function that we're looking for is a function of j, right? So I'm interested in the functional form of j, but this determinant of delta is a complicated thing, it's perhaps even infinite, but I don't care. This is all some other normalization constant that is independent of j. This is the only thing that depends on j, because b is ij. And so here we'll get 1/2 b transposed and A, which is delta minus 1. And then I squared gives minus 1. So this is minus a half j delta minus 1j. Yes?
The result of these integrals, isn't it a minus 1 an exponent? Or
I'm sorry?
isn't it B transpose a minus 1b? That's what you call delta.
Right. Yeah. Sorry. Thank you. Yeah. So it's a minus 1 in here. Indeed. I mean, here you get delta. Yeah. Right. Because, yeah. So all in all, we get another constant. So this has n, 2's, i's, and determinant delta. And then E minus a half j delta j. Right? And then what's this j delta j? Well, you have to remember what this x stands for. So in our case, it's a series of q of t i's, right? So this is a column vector. But the column vector we're describing in here is the series, remember, that integral is over q of t i's. So del q is product y dq of ti, right? So the product vector is really q of ti. So when we write something like this, or like this, I mean the double sum, where this would be an I, this would be a j, q of ti, q of tj, right? Or in other words, translating back into q of t, a double integral, right? So j delta j is therefore this double sum or double integral j of t delta of t and t prime, j of t prime, right? Here I just wrote the continuous version, but this would have been j I delta I j j, right? Okay. And then, who is this delta of t minus t prime? Delta of t and t prime. So delta and t and t prime, well, it's not, it's equal to. So we have to remember, so this was delta minus 1. That was our definition, right? So our definition, not quite, with an I. So IS was equal to this. So whatever, I times this would be equal to delta minus 1. So actually, I'll first write the answer and then I'll tell you why. Okay, so another way of saying it, I could put here minus b squared and minus b squared plus omega squared, right? And minus y is 1 over I. So in here I would get then 1 over I omega squared minus b squared, right? So I omega squared, and then this d squared dt squared in momentum space becomes minus b squared. Okay, so this is the right thing, Fourier transform. I just Fourier transform that. But we can check explicitly that we get the right result because we can act with delta minus 1 on this guy and see if we obtain a delta function, right? So if I act with delta minus 1, where delta minus 1 is I d squared dt squared plus omega squared on this thing, I dp over 2 pi minus ip t minus t prime over p squared minus omega squared. d dt acting on here gives a minus ip, and squared gives minus p squared, right? And I times I is minus 1, so minus p squared plus omega squared times this integral minus ip t minus t prime, then divided by p squared minus omega squared. And as you see, these all things cancel, and I'm left with the integral dp over 2 pi times of the exponential, which is nothing but delta of t minus t prime. Okay? So this is indeed correct. Okay, so my delta t minus t prime is this form, but but now we must do some more things. So first of all, excuse me. So first of all, the first observation is that this integral is singular, right? At t is plus minus omega, right? Has a pole. The integral has a pole. But that's nothing unusual. We have seen before how to deal with these things. We have to just deform the contour of integration over p from the real line to some complex line that avoids the poles. Right? In fact, we know that that one possibility would be to add here some I epsilon in the denominator. So you will see that this is the case. But before we do that, let's think about what this thing means. What have we done? We've inverted this operator that acts on a set of functions, right? All right, so let's be more precise about things. So we invert delta minus 1, which was I p squared plus omega squared, on a space of QFTs. Right? That's what we are trying to do. But before we do that, we should ask, is Q of t, is delta minus 1 of t invertible? And now comes the crucial point. When you say that you can invert an operator, you always have to define its domain. It could be that the operator is not invertible over the whole possible domain, but over its domain of definition it could be invertible. So the question is delta of t invertible on the whole Q of t's, or only some of them? Now, is this invertible on the whole space of Q of t's? How would you decide? If an operator is invertible over the whole space of functions or over some domain. Well, when is it not invertible? Let's say, put it this way. Well, 0, when it's 0, right? 0 is not invertible. So that's the only question. So the question is, in other words, has delta minus 1 q of t equals 0 a solution on the domain? That is really the question, right? But this is, by definition, I d squared dt squared plus omega squared, right? So, is this non-zero in general, or is there a solution for this?
There's a solution.
There's the classical solution. So not only is there a solution, but the classical solution satisfies this. So classical solutions satisfy this. Okay. So this is not a pathological case that could say, we'll just ignore this because it never happens. No, this is the most relevant case possible, the classical solutions. So we must do something. It's not an obvious thing. Okay, we can't just neglect this. So then, in order to invert delta minus 1, it means that we have to find a way to avoid the classical solutions. So we must define a Hilbert space without the classical solutions. So now this is some path q of t, right? And we want to define paths that avoid the classical solution. Now, the only possibility to do that is to put some boundary conditions that avoid them. Okay? That's really the only possibility. So we must impose some boundary conditions on the space that we wish to invert this operator, such that we have no classical solutions here. And it's not surprising, but we will argue that the correct propagator is the Feynman propagator. So, as before, I write I p minus I p minus t prime, and then p squared minus omega squared, and then I write plus I epsilon. So, why is this the Feynman propagator? Remember what we had before for Feynman propagator? Well, in 4 dimensions, we wrote minus I divided by p squared plus omega squared minus I epsilon, right? This was delta f of x minus x prime. But then p squared was minus p0 squared plus p vector squared, right? And in our case, so if I dimensionally reduce, if I ignore the spatial directions, I would get minus p0 squared, right? And then in one dimension, p0 is the only p that I have, so I call this minus p squared, right? So for quantum mechanics, I get minus p squared. So then here I have minus I over minus p squared plus omega squared minus I epsilon. That is plus I over p squared minus omega squared plus I epsilon. Okay. So I have really the same thing. All right. So let's also try to understand from the point of view of more general theory. So we start with some operator called delta f minus 1 with some eigenfunctions. It will have some eigenfunctions qi of t corresponding eigenvalues lambda I different from 0. That's what I want. I want to eliminate the 0 eigenvalue. And moreover, these eigenfunctions in principle have to be defined such that they are orthogonal. So that means that integral qi of t star qj of t should be delta ij, right? That's what it means to be orthonormal. And then, in general, by the general properties of operators, of invertible operators, I should be able to write the operator itself. So perhaps it's better to write first the general form. So if I have some operator A with some set of eigenfunctions Q and corresponding eigenvalues AQ, then so this process of diagonalization in terms of eigenfunctions and eigenvalues means that I can write the operator A as sum of the eigenvalue times eigenfunction times eigenfunction's Hermitian conjugate, right? That's a general property. That's what means diagonalizing an operator, really, right? So, having in mind this general theory, then if I find these eigenfunctions, then delta f minus 1 should be able to be, I should be able to write it as sum of I, lambda I, then qi of t, qi of t star, right? And then, moreover, this form is manifestly diagonal. So now inverting it just means inverting the eigen values, right? So then delta f of t and t prime would be just sum of I, 1 over lambda I, qi of t, qi star of t, right? Okay, so that sounds...
Sorry, but where's the t prime dependence there?
Yeah, okay, t prime. Thank you. So, now, the question is, are we in this form already? Is our delta minus 1 of this form? Well, so, or in other words, so let's consider already the final result. So delta F, is this something of this form? And let's consider our guess for the final propagator, which we know is the correct final propagator in one dimension. So we look at this thing, and is it something like what I wrote here? So Q of t, Qi star of t prime, and then some eigenvalue. Well, it kind of looks like this. So I have e minus ipt times e to minus ipt prime star, right? So that's hopeful. So I have that this looks like this, right? Then sum over I is something like this integral dp over 2 pi. So p is the parameter I that I was looking for, right? And then by this logic, I would have that everything else, so this thing is the lambda I. So lambda I minus 1, sorry. Like 1 over p squared minus p squared minus omega squared plus I epsilon. Right? So lambda then is equal to just this. Okay, so that looks certainly promising.
And the I.
Oh, there's an I as well. Well, okay, yeah. Yeah, so how should I say it? Minus I like this, right? All right, so that certainly looks promising. So then the first observation is that already looking at this general form, you see that if all Qi of t go to as t goes to plus infinity to the same function, then so does delta f, and the same thing at t going to minus infinity, right? So in order to understand what is the space, so remember the logic is the following. So I made these identifications on on delta f, which was my guess. Right? Now I want to prove that this guess is correct. So first I noted that if this guess is correct, then if all the Qi's at infinity go to the same function, so does delta f, and same at minus infinity. So now let's see, therefore, what is the behavior of delta f at plus and minus infinity, and therefore define Qi's of t's as having that behavior. Right? So to do that, we must calculate this. But in one dimension, this is easy, right? I mean, you could do it even in 4 dimensions. So, but in one dimension, it's certainly easy. So first case, if t minus t prime is positive, right? Remember, we are considering integration in the p-plane. So the poles are So the poles are at p squared equal to omega squared minus I epsilon. That is, p is omega minus I epsilon over 2, or so plus omega or minus omega plus I epsilon over 2, right? So the poles would be plus omega minus I epsilon over 2. And minus omega plus I epsilon over 2. And then in this logic I integrate with a real line. Okay? And then the integral has also this factor e minus ip times something positive, right? So as you remember, the issue is to where do we close the contour. So if I close the contour below, then the thing in here, then p will have a negative imaginary part, right? So this is the minus I times something. But then with the minus I, this would be minus, and here positive. So this would be a decaying exponential, right? So that means that indeed, by closing the contour below, I get a decaying exponential, means that no contribution on this integral below. Okay. So if t minus t prime is positive, that means that I close the contour in this way, and then by the residue theorem, I get only the pole at omega minus I epsilon, but omega. And then I'm left with what? So p replaced with omega. So by the residue theorem, I get that delta f t prime is so the residue gives 2 pi I, 2 pi gets cancelled. Here I get a minus. Let me see if I'll get things correctly. So minus sign, then e to minus I, p is replaced with omega, then t minus t prime. Yeah. And then here p squared minus omega squared is p minus omega, which is, so I'm looking at the pole p equal omega, so that part I erase. And then p plus omega. Oh, and I get the wrong sign. Because this would give me a factor of 2 omega. I think I got the wrong sign. Why did I get? Residue theorem. Oh, right. The contour of integration is clockwise. It's anti-clockwise is with a plus sign. So that's why it's a plus. Sorry. Yeah. It's clockwise, it's a minus sign. So I had the minus with another minus is plus. Right. So this is for t greater than t prime. And then for t minus t prime negative, right, t minus t prime negative, then I have to close the contour the other way, right? I have to close the contour like this. and then I pick up the other residue at minus omega. In this case, delta f of t minus t prime is, I get 2 pi I, which gives me the same minus, but now the sign is anti-clockwise, the contour is anti-clockwise, so that doesn't give an extra sign. I just have the minus. Then e to minus I, but then p is minus omega. So I have minus omega, but then t minus t prime, which is negative, and I prefer then to write this as omega absolute value t minus t prime. And then in here I have again p minus omega p plus omega, but now the pole is at p minus p plus omega equal to 0, so I remove this and I'm left with this. And at p equal minus omega, this is minus 2 omega. Okay? So all in all, we see in both cases I get that delta f t prime is e minus I omega absolute value t minus t prime over 2 omega. Okay? So that's the result of this calculation. And now let's come back to our question. We want to see what's the behavior at t going to plus or minus infinity in order to deduce what was the behavior of the functions qi of t at t going to plus or minus infinity. So at t going to plus infinity, we get that delta f of t in t prime goes to, behaves as, so the point is that t, is not even behaves as, but there's some constant that depends on t prime and omega, and then e minus I omega t for t going to infinity. So for t going to infinity, that means that t minus t prime absolute value is equal to t minus t prime, right? But now, at t going to minus infinity, the only difference here is that absolute value t minus t prime is equal to minus t plus t prime. Right? So that means that delta f now goes as e to the minus I omega times minus t, so e to the plus I omega t. Okay? But now, by the logic that we had in here, that means that we can deduce that the space of functions, the space of eigenfunctions for the operator delta f minus 1 was such that qi of t okay, let me erase it. Was such that the space of functions qi of t on which delta f minus 1 is inverted satisfies qi of t at t going to plus infinity goes to e minus I omega t, and qi of t at t goes to minus infinity goes to e plus I omega t. Okay? All right. So now we finally understand something about the Hilbert space. Okay? So let me erase this now. Now we understand that the space of functions over which you invert is such that minus infinity is e to the plus omega t and the plus infinity is minus e to the minus omega t. Okay? So that's certainly promising. Different behavior at the two endpoints, which suggests it's not the same function. Now, of course, the operator that we were interested in inverting, I d squared dt squared plus omega squared, on both of these things gives 0, right? So both of these things are solutions of the operator, of the classical equations of motion of the operator at plus and minus infinity. It's just that the solution, but qi of t will not satisfy this in the middle. At t different than plus or minus infinity. Right? That's the whole point, that if the solution would behave the same way, either at e to the plus I omega t at both, or e to the minus I omega t at both, then it would be possible to find a solution that satisfies this everywhere. But since on one end it's one, and the other end is the other solution, that means somewhere in the middle it will not satisfy this. So this is a correct space of functions for inverting the operator. Okay? All right. Okay, so now that we've defined the space of functions, let's see how we define the path integral. So then, the path integral is defined in terms of, so I can define this as, so remember I have to I have to path integrate over q of t, right? But the classical solution that I choose is one classical solution. So let me write this then as, so this satisfies now the correct boundary conditions. So this is the variable in the path integral has to satisfy the correct boundary conditions, this. And I write this as a classical solution that satisfies the correct boundary conditions. Classical solution depending on t and j, right, plus a fluctuation that satisfies zero boundary conditions. That means it goes to zero at both ends. Okay. So our action, our Gaussian, the action in our Gaussian path integral was written like 1/2 xax, and then plus jx. But then I want to think of this as, so x stands for q of t. Right? But then I want to consider this classical solution as some x0, and then this variation as x minus x0, right? So I want to write this as x s of x0 and j plus a fluctuation, a quantum fluctuation, that is 1/2 x minus x0 a x minus x0. Okay? Because this is a classical fluctuation, it's a minimum of the action, right? So that means that the quantum part, the quantum part will enter only quadratically, so I automatically must have this form, right? And then, if you note, this thing will be independent of j. So this is s of x minus x0, but 0.
Sorry, Professor, could you repeat why we will only have quadratic part on this quantum fluctuation?
Well, because this is ds dx equals 0 implies x equals x0, right? That means that this fact means there's no linear part in x, right? That's what this says. It's only quadratic, right? Okay. So that means that in our case, right? So that means that in our case we write s of q and j is s q classical and j plus s of delta q and 0. So then the path integral z of q and j is integral dq e to the I s q and j. I mean, okay, this is a, yeah. I just put q there in the sense that it's a path integral, but it explicitly depends only on j. So this is such a path integral, but by substituting this form, I get this outside, since the path integral now is only over delta q. So I get e to the I s of q classical and j. And then the path integral itself is only over this delta q, e to the I s delta q and 0. But as you see, this is independent of j now. This is j independent. That means it's part of n, right? Part of the normalization factor. So that means that z itself is only equal to this. And then the classical equation of motion, remember, is delta minus 1. Delta minus 1 is the operator. So I had minus a half q, delta minus 1 q, plus ij. This is what I had in the exponent, right? So then by variating this with respect to q, I get that minus delta minus 1q plus ij equal to 0. Because delta minus 1q classical is equal, this was q and j, is equal to ij. That's my classical equation of motion. Right? And so the solution to this would be so I act with the operator, I think of this, so now that I'm talking about invertible operators, I'm allowed to act with them and cancel them, make identity. So acting with delta on both sides, I see that we obtain the term I delta j. But then in principle, anything that solves delta q is 0, because then if I can add it for free and obtain the same result. So this I would call q classical of t and 0, right? This is the solution, the classical solution in the absence of any force. So a 0 mode. Okay. So, yeah. Delta minus 1 q classical q 0 is 0. Okay. Though, of course, as you should have probably noted, then this doesn't satisfy the correct boundary conditions. Right? So, doesn't satisfy correct boundary conditions. But that's fine, right? Sorry, plus. But that's fine. The point is, this thing satisfies the boundary conditions of this thing. So this one has the wrong boundary condition, but this has the right boundary conditions, right? Because this starts with delta, so delta dot j means of t is delta of t prime integral t prime j of t prime, right? But that means that for t going to plus or minus infinity, this has delta of t prime behavior, which is correct, right? So this has trivial boundary conditions, right? This is a 0 mode, the one that has trivial boundary conditions. Then finally, the variation of this S of Q classical and J with respect to J can be written as partial variation of S with respect to Q at Q is Q classical times the variation of Q classical of T and J with respect to J. Right? So Q classical depends on T and J, but in here I have an implicit dependence of J and an explicit dependence of J. So I'm writing this as the variation, by the chain rule I write this as a variation in respect of S with respect to Q, and then of Q classical of T and J with respect to J, plus the direct variation, the explicit variation of J, so delta partial S d J of T, right? And I have to integrate over T prime because I have two functional differentiations on the right and one on the left, right? So the chain rule for functional differentiations must necessarily involve an integral because the functional differentiations removes an integral, right? So here I remove two integrals and here I remove only one, so I have to add one more, right? However, this is just 0 by the equations of motion, right? This is just 0 by the equation of motion. Because at the end, I put Q equal to Q classical, right? I have to in order to take this second term. So that means that in effect, I have only this second variation. But this second variation is equal to Q classical of T and J, right? That's what this means, right? So so that means that delta S of Q classical and J respect to delta J of T is Q classical of T and J, which itself was the zero mode Q classical of T and 0 plus I delta dot J. And now that I have this differential equation, I'll integrate it. So I integrate over J of T. And finally write write that S of Q class S of Q classical of J and J is so when I integrate, I guess a term that is Q classical dot J, a term that is I delta J J, 1/2 delta JJ. But then in principle, I can also get a constant, right? And I'll call this constant S of Q classical of 0 and 0. So this is a constant of integration plus Q classical of 0 times J plus 1/2 J delta I delta J. Okay. All right. So now I'm in position of writing Z of J, right? Z of J was e to the is Q classical J, this thing I just calculated. And then the integral itself, the integral that remained in here was just something part of n, which I didn't care, right? So then finally, I write that Z of J is n doubled because I add yet one more thing in it, this integral, this path integral, and then e to the I times this, right? And this thing is independent of J, so this is also part of n double, right? So the only non-trivial things are these two terms. And this is what we had before. So I times I is -1, so it's -1/2 j delta j. This is what we had before. But now I get one more term. I get plus I q classical of 0 dot j. So now we'll see that we have a new term due to boundary conditions. Okay, so this was this zero mode that we needed to introduce. This is a zero mode that needed to be introduced because of boundary conditions. Okay. So all of this was a very long, sloppy treatment, and the point of it was to really to introduce a little bit more the physical significance that we have, I don't know, physical or mathematical significance, I don't know how to call it, but the point is that we needed to invert on a Hilbert space that avoided the classical solutions, the zero modes. And then we had to introduce some boundary conditions. And the final result of all the analysis of the boundary conditions was an extra term in the path integral, which in retrospect could have been thought of as the result of partial integrations, of carefully taking into account which result, which part of the action is correct when we consider a domain with given boundary conditions. But this is not very rigorous. I mean, you see that there are various points where we had to use some approximations. So instead of this, I now come to the correct treatment. Using the so-called harmonic phase space. So this is a modification of the phase space path integral that will be called harmonic phase space. So since we're talking about the harmonic oscillator, the Hamiltonian for this was p squared over 2 plus omega squared q squared over 2. And then we know that we can make a transition between q and t and p and t, q of t and p and t, to a and a dagger. So this was just a change of variables in some sense. Here we have a minus a dagger, sorry, a plus a dagger, and here a minus a dagger. And reversely, we wrote a and a dagger is 1 over square root 2 omega q minus ip, and omega q plus ip. And this itself depended on time as e minus omega t, and plus I omega t. Okay, so this was what we did before. And then in terms of this A and A dagger, the Hamiltonian was omega A dagger A, right? So this would have been, so this transformation was at the classical level. But remember, the classical level is also, I mean, the classical Hamiltonian is also what appears in the path integral in the phase space. That is what we initially had. So in principle, we could also think about using it there. Now, in quantum mechanics, of course, we replace A and A dagger with operators. And then we have that A and A dagger anticommute with 1. And then, moreover, we define the Fock space representation, or, well, in the case of a single one, let's say the number operator representation. Fock space would be in the case of several oscillators. So we had states that were obtained by acting with the A dagger on a vacuum, right? So A dagger to the n over square root n factorial acting on a vacuum. Okay, so this was a set of states for the harmonic oscillator, a basis. So the basis was defined as the sum of all these states n. However, it turns out that there's another basis that is useful, the basis of coherent states. So these are states that are considered. So you see here, these states are obtained as the A dagger to the n over square root n factorial acting on the vacuum. These are characterized by n. But if I sum over n and I put n factorial instead of the square root, I would get an exponential. And in principle, I could put also another parameter alpha in here. So then I would generate this states e to the alpha A dagger acting on 0. In other words, this being alpha to the n over n factorial A dagger to the n acting on 0, right? So therefore, this is a linear combination of the n states. So this is another kind of basis, right? If I have a general alpha, I can decompose any state that was decomposable in terms of these, also in terms of these, right? So this is a new basis. So what's the usefulness of this? Well, the usefulness of these states is that they are actually eigenstates of A. These are eigenstates of A. Right? A is called destruction operator for the reason that it creates, it shifts the number n. It creates an occupation number right? So it's not an eigenstate of n, but here we define it's not an n are not eigenstates of A, but alpha are eigenstates of A. They are combinations of these states that are eigenstates of A. So to see that, first of all, I write this as e to the alpha A dagger acting on 0. And then I can, for freely, write this as A commuted with alpha A dagger acting on 0, because the extra term is this, and this is 0, right? So the extra term I've added is the one with the opposite order, where A acts on 0 and gives 0. But now, in this thing, I can calculate this, so I can expand this is A, let me write it like this, so sum over n, alpha to the n over n factorial, and then A commuted with A dagger to the n, right? Just that this thing would be equal to what? So I can rewrite this as A. So if I can commute term by term. So here I have n A daggers, right? And I can each time commute only over 1, right? So I write this as A dagger, A dagger to the n minus 1, plus A dagger, A dagger, A dagger n minus 2, plus dot, A dagger n minus 1, A dagger, right? Because so the first term is the correct one without the commutator. Then the second term is minus A dagger n minus 1. But then from this term I have the same term with a plus A dagger n minus 1, right? So these two cancel, and then the second term in here cancels the first in the next, and so on, right? So all the extra terms cancel, right? Is everybody clear on that? Maybe you should write okay, let me write one example with 2. So if I have just A dagger squared, this is A dagger minus A dagger, let me forget I have A, but then I chose to write it as A dagger plus A dagger, A dagger, right? Which is A dagger A minus A dagger A, but then plus A dagger A dagger, sorry, dagger, plus A dagger, plus A dagger A dagger, but then minus A dagger A. Then these two terms cancel, and I'm left with the first and the last one, which are the same, right? So I did the same thing here, just a bunch of times, right? Okay, but this thing is 1, A dagger is 1, right? This is 1 everywhere. And then outside I still have only A daggers, right? So all in all, this thing is equal to n times, so this acts like differentiation, really, right? This is n terms A dagger to n minus 1, right? So, and then the n cancels. The n cancels with 1 in here, and I'm left with A dagger to the n minus 1 divided by n minus 1 factorial. So this is almost the same exponential, except now I have alpha to the n, which I rewrite as alpha times alpha n minus 1. And now in the sum, I have the remaining thing. So this is indeed alpha times e to the alpha A dagger. Okay? So all in all, then A alpha is alpha A dagger 0, which is alpha. Okay, so this is what I wanted to prove. Right? Okay, so the coherent states are eigenvalues of A. And then of course it's obvious that I can take the dagger as well. So I can define alpha star as being 0 E alpha star A, right? I mean, I just take the dagger of the relations before, and then by that, obviously this is alpha star, right? And now the product of these two things, of the bra and the cat, can be written, for instance, writing this 0 into alpha star A acting on alpha, right? Just a moment. So this now is equal to sum over n alpha star A to the n over n factorial acting on alpha, but A acting on alpha gives alpha, right? So then this replaces A with alpha. So this is equal to sum over n alpha star alpha to the n over n factorial. So this is e to the alpha star times the sum alpha, right? So this is equal to e to the alpha star 0 alpha. But this itself is 0 E alpha A dagger acting on 0. But now this itself is I can think of dagger of e to the alpha A acting on 0 if I want. I mean, I could use also this. It's the same, sorry. But anyway, maybe it's easier to try it this way. And then this itself is sum of n alpha n over n factorial a e n acting on 0, right? But this is sum from 0. And all of the non-zero terms, a acting on 0 is 0, right? So the only thing that remains the sum is the original 1. This thing then is equal to just 0, right? 1 times 0. In other words, this thing is equal to 0, 0, that is 1. Okay? So that means that e to the, alpha star alpha is e to the alpha star. Okay? And then, so this is about normalization of the coherent states. And they're also complete the completeness relation is kind of, the fact that they're complete is kind of obvious. As I said, the original number operator basis was complete. And this is sum of all the states in the number operator basis with arbitrary coefficients. So it's kind of clear it should be a complete basis as well. But the completeness relation itself perhaps is not entirely obvious, and I left it as an exercise. So is this one. Okay, this is an exercise. And important thing is note that the actual constant so the constant here depends on the definition of integral d alpha star. So you have to think about complex integration. There's some conventions. You have to think about how to take these conventions about the alpha star as opposed to integral over the real and imaginary axes themselves. Right? Otherwise, you might get a factor of 2 wrong also, or I, 2 or I wrong. All right. So now we want to calculate. So remember the point about introducing the coherent states was that I wanted to define better the path integral. So in order to define the path integral, we do the same thing as in the representation of Q of t. Namely, we consider transition amplitude, and then we write it, we discretize it, and write it as a path integral. So the transition amplitude that we'll consider, however, now has to be, instead of from state qt prime, q prime t prime, from state qt to state q prime t prime, now it has to be from Heisenberg state alpha and t to Heisenberg state alpha prime and t prime. Right? So I'll call this alpha complex conjugate, by which I don't mean necessarily complex conjugate of alpha, but and this is not a, well, I hope the notation is not confusing. I don't mean this is complex conjugate of this, so not complex conjugate of alpha in them. So alpha star t prime with alpha t. And these are Heisenberg states. So that means, as before, in terms of Schrödinger states, I would write alpha star e minus I h e minus t prime alpha. So these are Schrödinger. So now we need to write a Hamiltonian with a driving force, with driving forces. Just that the driving forces, I have to write them in terms of A and A dagger, right? So I will write H of A dagger A and T as being the Hamiltonian in the absence of driving, omega A dagger A, minus forces J of T for A dagger, and J bar of T for A. But of course I want this to be the same as before. So I want the driving term to be the same as before. If J of T is real. So in order to do that, so I define J of T as capital J of T over square root 2 omega, and the same thing for J bar. And so if J is equal to J bar, in other words, the source is real, then I would write that J of T A dagger plus J bar of T A this is equal to Q of T J of T, and in order to remember that, in order to see that, we remember that A of T was omega Q minus IP square root 2 omega, and so A dagger of T omega Q plus IP square root 2 omega. So if I multiply with J of T and J bar of T, J of T, J bar of T, then the sum, and if I said if J is equal to J bar, then also little j is equal to little j bar, and so in the sum in here, the terms with plus IP and minus IP cancel. Then I'm left with the other terms. So this is equal to square root 2 omega q little j of t. But j of t is capital J over square root 2 omega. So I indeed get qj, right? Okay. All right. So this is then our driven Hamiltonian. And moreover, let's see how it acts, this Hamiltonian, on the coherent states. So the thing that we have is in between an alpha star and a beta. So alpha star h of a dagger a t, beta is alpha star omega a dagger a minus j dagger minus j bar a beta. And in the first term, a dagger acts on alpha star and is replaced by alpha star, and a acts on beta and is replaced by beta. And here, a dagger acts on the left and is replaced by alpha star, and here a acts on the right and is replaced by beta, right? So all in all, we obtain H, where I just replace a dagger with alpha star and a with beta, and then alpha star beta. And then moreover, this thing itself, we've calculated it to be e to the alpha star beta, right? Okay. So we have the Hamiltonian, we have the action on the state, so now let's write the path integral. And for the path integral, as before, we divide the path in n+1 intervals. Divide t equal t0 to t prime equal to tn plus 1 in n+1 intervals. So here we have t1 until tn, right? And then epsilon is t minus t prime over n+1. And as before, in order to calculate the path integral, we need to insert the identity written as a completeness relation in between many divisions of the exponent. So the exponent is e minus I h t minus t prime, right? And then this is equal to e minus I h t0 minus t1 plus t1 minus t2 and so on till minus tn plus 1, right? And so each of these terms is epsilon, but understood as moving forward in t, right? So this is an e to the minus I epsilon h, another e minus I epsilon h, and so on, e minus I epsilon h, right? And everywhere I insert the 1, but written as the completeness relation. The completeness relation I left for you to prove, which was that 1 is equal to integral d alpha star over 2 pi I e to minus alpha star, alpha star, right? Okay, and but now for each of these things I consider a different time, right? So for each of these things I consider the corresponding so for each of these things, I consider a corresponding Ti and Ti, right? And then, so then in here, let's say I have T1, then here I have T2, until here having Tn, right? So then in the end, I obtain that m of alpha star t prime alpha t so each integral is over a different t I, so d alpha ti, d alpha star ti over 2 pi I, then product of all these integrals. That would be my my new kind of path integral. And then moreover, each one will come with e minus alpha star ti alpha ti. Right. This is from the all the identities that I've inserted. And then here on the left I had alpha star of t prime. Then I have e minus I epsilon h. And now I have these insertions of the identity, which came with alpha of t1. No, sorry, t prime is to the left, so this is tn. Alpha star tn, alpha tn. No, what am I doing? Alpha star. Yeah. And then e minus I epsilon h. Now the same with tn minus 1. So alpha of tn minus 1. Alpha star tn minus 1. Minus I epsilon h. Blah blah blah. Until let's say alpha of t1, alpha of t1, e minus I epsilon h, alpha of t, so it's t0. Okay? All right. And now in each of these terms, because they are of order epsilon, remember how we did the trick, we write this as minus 1 minus I epsilon h, right? And because I neglect terms of order epsilon squared, I consider only linear terms. And then for this thing I have alpha star h alpha, for which I've noted that I can just replace a dagger with the alpha star and a with the beta, right? So when I write it like this, I can replace h of a dagger a and t becomes, so in this one it will become h of alpha star t prime, alpha star of t prime and alpha of tn. And then I redo the exponential because again we're only working on order epsilon. Right? So in each of these exponents, I basically take it out and rewrite it as rewrite the corresponding term as the classical value where I replace these things, and then the product of these two things. The product of these two things is e to the alpha star beta. So let's say that this first term becomes e minus I epsilon h of alpha star t prime alpha tn, and then e to the alpha star t prime alpha tn, right? And then all of the other terms go like this until this one is e minus I epsilon h of alpha star t1 and alpha t, and then e alpha star t1 alpha t. Right? Okay. So then I can finally write for the amplitude. I have this this measure. Then in the exponent, I have what? For each of the term, I have for each integration, I have a term e minus alpha star ti alpha ti. But then I also have these terms coming from the products, from this times this. But here I have alpha star t prime, alpha t, and so let's write the correct term. So alpha star t1 alpha alpha star t prime alpha t1, and then minus, so this is this, and then minus alpha star t1 alpha t1, then plus alpha star t1 alpha t2 minus alpha star t2 alpha t2 dot 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 until sorry, I got confused in my own notation. There was n, right? Here to the left was n. This is n. Sorry. N. N. N minus 1. Then I want to write n minus 1. N minus 1. Until alpha star t1 alpha of t, which is t0, minus, no, that's it, right? Yeah. This term stands alone. So here I have terms canceling, but here I have a term standing alone. And then now I have to collect the h terms, so this minus I epsilon h. So minus I. And of course, epsilon is dt, which in this case stands for, let's say, t prime minus tn, right? The difference between the two. And then, as before, when you do the path integral inside the Hamiltonian, I can approximate to order, since this is already multiplied by epsilon, the difference inside the Hamiltonian of the two times is of higher order in epsilon. So I can put in the Hamiltonian the same time, right? So then, this is minus I times integral from t to t prime. And here I have just h of alpha star tau, alpha tau, and tau. Right? So once again, in here in principle I would have different times, but they would be different by an epsilon, which is higher order than epsilon. Epsilon is dt. So I didn't care about that. Okay. So what we see, what do we get here? We get, so it's the same alpha of t, and then we have alpha star of t prime minus alpha of tn, right? But this is what? This is basically alpha star dot of t times dt, right? So so in here, we have basically integral dt, alpha of t, alpha star dot of t. So this is the sum of all these things, so that converts to an integral from t to t prime, and well, let me call it as before, tau, these terms. And then we still have this term that is left by itself. So all in all, we get that m of alpha star t prime alpha t is this path integral that I decide to call d alpha star. Okay. And then exponential integral t prime d tau, then alpha star dot of tau alpha of tau minus I h of alpha star tau alpha tau tau. Then outside the integral, alpha star of t alpha of t. Okay. And well, I guess yeah, one other thing we can do is to put the I outside. So write it I in here, then write minus I in the first term. Okay, and this is the final result for our harmonic phase space path integral. Okay. All right, so in principle we're not done. So we have defined the path integral, the basic path integral, but we have not calculated what we wanted, the partition function. So I will finish that next time and consider the implications of that. But for the moment, we have defined at least the harmonic phase space path integral. And note that this is well defined. So up to now, we have not obtained any issue with boundary conditions. All right, this is everything I want to tell you today. Do you have any other questions? They go to zero, yeah. All right, that's everything. Yeah, you can stop. So for the exercises from last week, see that happily great majority of you